Hello, welcome to today's stream. We're going to be talking about DMA on the ZCU and the PYNQ. So this is kind of a continuation from yesterday where we ended short because the bit file took a long time. And to continue on to that, because they are using proprietary HDMI PHY and transceiver receivers, my bit file actually didn't finish. I need to get the license for that to get that to work. So I went ahead and just did a quick DMA version so we can go through it. And you can learn how easy it is to develop on the PYNQ. And I'm going to show you kind of some base memory addresses, so if you ever want to create your own hardware and whatnot, you don't have to rely on the PYNQ software. That being said, the PYNQ does have a lot of powerful software that I haven't used much, and it's might be a little bit difficult to understand how it goes, but from what I tried today, it was super quick and super easy to get that going. So let's get moving. Get DMA on the PYNQ. First, we need to get the hardware going. So I created this you remember last time there was a full screen of IP cores that were on the ZCU device. Today we've minimized it, so I have buttons, LEDs, and then we have a DMA device. And this direct memory access, DMA, is looped back onto itself. The only changes I really made to this design is I gave it 40 bits of addressing. That's because the MP-SOC has 40 bits of addressing, so if we ever want to do DMA across that, we potentially could. But in this situation, I don't think we can, because if we go look at our address editor, the only values that are available on the on our DMA is the DDR and the QSPI. So, and we're only accessing the DDR, and the DDR low value is 2 gigs. I'm not sure if we have an upper value for DDR, but this is basically the address we care about is the DDR low. Being able to read and write the DDR. That's the most important part. And then we have a smart connect connected to this slave port, and a master port connected to the buttons and LEDs. So how do we get this bit file onto our PYNQ? Very good. So we go ahead and just generate the bit stream as normal. So let me pull over our little thing, and I named these LEDs. I mean, it's DMA, but we named it LEDs. So the files you need are LEDs bit, LED hardware handoff file, and I'll show you the PI file. It's really simple. I just copied the base overlay and removed some stuff, so it's fine. And a knitpy, and you just have this in the overlay folder under the PYNQ folders, and it's not too hard to figure out where to put this. So we can generate the bit file through Vivado, but now let's figure out how we generate the hardware handoff file. And the way I found this, so let me show you. If we go actually, let's keep that there so we can show where that is. Let's create a new folder. Just open that file location and then go up, up, up. No, that's not where I wanted to go. So I guess we can make this a little bit bigger. Go to C drive here, PYNQ 2.5. We go to boards, ZCU104. Go to base, and if we go to this build bit stream, right? Let's get that in a lovely little window over here. Boom, boom, boom. So if we look at this thing, the hardware handoff file, this is the other file we need. If we look, it's overlay name, sources, under the block diagram, under handoff files, and then we get the handoff file. So there's not an easy way to generate this. It automatically generates it with the block diagram, but you have to go hunt it down. So if we open up this guy, we look at the chain. This is under base, LEDs to the project, LED sources, block diagram, base, hardware handoff. I copied it from base, made it LEDs. So those are 2 files we need. And we just plop those into our mobile Xterm file and plop those onto the PYNQ. So now we need LEDs pi, and let me show you what we did for that. So here's base pi. This is their base diagram. It has PMODs, it has LED button switches, it has specific clocks for the HDMI, which is complicated because there's off chip, there's off FPGA chips that are generating the clock, so they have a bunch of configurations for that. So we copy that all over. We change names, LEDs, And we're only using buttons and switches right now, so we'll just keep it like that. Keep it very basic. And it automatically, so as you can see here, GPIO LEDs channel 1. You may be like, how does it know that? So let's, do we have the hardware handoff file? Let's open the handoff file. Where'd the mobile X term go? Oop. So let's go ahead and open this. Let's bring that over here. Oop. So the hardware handoff file, we have instances of GPIO LEDs buttons, and we have to tell you what, that's external ports, modules, okay. Let's see, yeah, bunch of information. Let's see if we can find what were we specifically looking for. We were GPIO LEDs. So Control F, GPIO LEDs. So we have instance names. We have a full name. We have the basics of what it is. And so what happens, it basically is your device understands this. A PYNQ, it loads this and automatically creates a cool library for you. So that's where these things come in really handy. So you can automatically set direction, set the length, very useful. And the other thing is the init.py file right here. And all you need to do is kind of from LEDs folder, import LEDs overlay. Pretty basic. So once we have all those files set up, we can interact through the PYNQ. So if we go here, I have a little register thing set up so far. So this is very similar to the base LEDs. So right here, we are able to, let's just go ahead and make this full screen. Let me pull up my stream OBS so I can actually see what's happening. So we can pull this up, and we're loading the LEDs bits into our LED overlay. So let's go ahead and just run this. Actually, let's go kernel. We're going to restart and clear output. Go ahead. Let's get a fresh start to life. Okay, so we run this, and it programs our board. As soon as the kernel's ready and it goes through. I guess we need to rerun this. I didn't see that say one. Okay, so we program the board. Now, you see I'm importing what's memory mapped IO. So if we go play around with memory mapped IO, that's going to be here. We have memory map io.py, and this is a system that allows us to pick a base address and allocate a certain amount of memory map space to read and to write to. Memory map, registers, and then we can read to it and we can write to it. The write. There should be a write somewhere in here. Oh, he just redefines the write function right there. If it's register or memory mapped. I'm not sure what the register. I'm not sure where that register comes into play, but we have a memory map we can read and we can write to. Very useful. So this allows us to access the addresses on our device. And this is what I use if I have some new hardware that the software isn't supported by PYNQ. I can just do direct memory reads and writes, and I'll show you around later. We're first going to do LEDs, and we can see the LED address is 8004600. So one way we can do is we can directly load that in right here. Or directly load the address in here for memory mapped. We can also, I believe, we can look up a dictionary. If I remember right, let's go look, see how they do the dictionary version of this. I think it's, we go to library and we go to RGB LED. Do they do the dictionary? So, let's see if we can look at all our values. So let's go ahead, insert below here. Nope, that's not what I want to do. Insert below. We also need to import PL, right? I think for this from PYNQ import PL, I believe is what we want, and I think we just leave that blank. GPIO LEDs. What is the IP name? GPIO LEDs, right? Well, let's just print out the entire dictionary and see what we got going for us. We have ANSI DMA. GPIO buttons. Is it below this one? So let's see, we do GPIO buttons. That's interesting. What was the name then? Oh, do I need to put like that? Okay. And what are they doing? They're doing, I don't know if this is even valid anymore. Physical address. I do see, there we go, physical address. Boom. And we can do LEDs, right? And let's go ahead, print hex. So there we go. There's another way we can get the physical address. So we can memory map. We memory map this device. We allocate 16 bytes to it. And then, so for our GPIO, let's understand what these registers we're writing to, because it's important to understand. So GPIO, is that the one we want? I just want. This is just the ANSI GPIO, right? This isn't anything fancy. Yes. Yeah, so let's go to my favorite portion of these things is the register space. So it's very basic. You have data and tri-state, and we already set the tri-state to output. So what we want to do is we want to write to address 0, and the first 4 bits are LEDs. And currently they're all off, and we hit this, we run this execute. LEDs, oh, I gotta run this one first. Run that, then we run this, and we see all the LEDs turn on, and then we see all the LEDs turn off. And this is a quick way to read and write to that specific address. Now let's play around with the LED feature here. So we already have LEDs kind of distinguished, right? So we can just go on. And so if we do overlay dot, what did we do in our thing? LEDs pi. So just LEDs. And we do LEDs and we off. And I assume this is like a mask. Let's do on first then. On. This is a mask, so we just do that. Oh, we gotta do has no attribute. How did they do it in this one? Base. Okay. Oh, we have to do register map, GPIO data, register map, GPIO data. So let's just see what this looks like, right? Channel has no attribute. What is this? This is an ANSI GPIO channel. Let's go hunt it down. I'm curious. So we're in library. We have an ANSI GPIO. And we have a channel. Value maybe? And is not callable. Okay. Oh no, that's not what I do. See, I have never really used this. We have a write and a read, so yes, we could just write mask. So a mask. There we go. So where is this? Is this in here? Right. Value. Okay, so we have a channel, right? This is what we got. Value and mask. Then we can read, so. I wonder how we defined it, because what did we say here? Oh, we go here. We set channel 1. Okay, so we took the LEDs channel 1, so it's now a channel. And so, yeah. So we can do this instead, and this is an easy way to allocate those values. So that was LEDs, very basic LEDs. Now let's look at doing DMA. So the first thing we do DMA, we need to allocate memory, place in memory for input buffer and output buffer. And PYNQ has this very nice way to allocate memory. So we have these NumPy arrays, uint32s, and they're 32 words long. We can print out the physical addresses here. Boom, boom. Then we can assign, we can print out the value for, write the value for the input buffer. So let me go ahead and insert a cell below. We got this guy, but now we want to do, what is it? Axi DMA 0. So here's the address for Axi DMA 0. Boom. And we're going to allocate hex 60 bytes to read and write to it. So this is MM2S control register, and let's put that there. This is the status register. Boom. And this is the S2MM control register. And this is the S2MM. Okay, so let's explain what those things mean. Actually, I'm gonna run that one first. This is memory map, or main memory to stream. I'm not sure what the actually M stands for. Let's see, does this actually say what that means? I always think of main memory or something like that. Let's see if they're first, they define that. Okay, memory map to stream, that's what I thought. Either memory map or main memory. So but let's go back to that register. Be important. So let's see, I go ahead and get this up here. So how well can you see that? You can't see that at all. we'll walk through it. There we go. So we have map memory to stream, control register, map memory to stream, status register, and then stream to memory map, control register. So these are important. So let's go figure out what these values mean. What we do is we go hunt in the documentation, we go to where the register space is defined. And so first let's look at the control register, right? So we have bit 1 is on, which is reserved. That bit was always read as 1, so that's fine. And then we have bit 16, so we scroll down to bit 16 right here. And this is just the IRQ threshold. I'm not using IRQ in this example. Right here, the field is ignored when we use for direct register mode, so we're good. That value is not important. Next, we have our status register, and bit 1 is high. Bit 1 being high means the device is halted and the DMA channel is not running. So it looks like our control and status registers are good to test out our channel. So let's go ahead and print out the output buffer. The output buffer is all set to zeros. We haven't transferred yet. So if we go down where we want to go, we go down the programming sequence right here. We can talk through what is needed to get our device to work. So first we're doing the read. I like to set up, we're doing the write first. Oh, we're doing the write first. We'll just do the write first then. So here are our 4 steps to doing the write. So first we want to start off by writing a 1 bit to the control register. So I'm writing a 1 to the control register right there. And we skip step 2 because we're not doing interrupts. So in step 3, we want to configure the address, and we have a lower and an upper address. So the upper right now is 0. I don't think that ever is going to change. And then the lower address for the read, or the write from DDR to PL, is going to be our input buffer and device address. And we printed that out right here. So it's just going to put that address into here. And we're going to write that to this register, which is the lower address register. And then you don't have to use magic numbers. You could potentially define it and whatnot. Next, we want to write the length, and the length in bytes is going to be 32 times 4 because we have 32 words. And that's it for doing the write. Now for the read, it's going to be S2MM. We're just going to do the same actions, but for that channel registers. So we're going to enable it, upper address, lower address, and we're going to use the output buffer this time. And then we're going to write the length in bytes. Okay? And that's all in the Xilinx documentation of how to run that. You don't need driver software. You can do some register poke and prodding to be able to do some simple DMA. So we go ahead and we can run it. And if we go here, we can see that the status changed, that it's running. And let's go check out what that bit means. That's going to be bit 2 of status. And bit 2 of the status means we are idle. And for direct transfer register mode, DMA, oh, you can't, can you see that one right here? DMA transfer is completed and controller is paused. So good, we complete our transaction. Now let's print the output buffer to prove that we did it. And look at that. We transferred the input, which was a count from 0 to 31, into the output buffer. We did DMA on the PYNQ. So next, let us change let's write this, so we do plus 0xF0. I want to just reset this. So let's see how the PYNQ does this, right? The PYNQ. So the PYNQ has some fun software. So all we need to do is overlay AXI-DMA0, and AXI-DMA0 is the name of our IP, which we can see here, AXI-DMA0. And we can just go ahead and set that up, give it a variable. And then if we go to their DMA tutorial page where they talk about allocating, whatnot, then they have this right here where you can send channel, receive channel, and to wait. So we go back to our channel here and we run this. And boom, no, boom. We now have different values. Let me go hex that so it's more entertaining. Boop. And we added F to all our values. So I had to go through, I had to read all the documentation to get this up running with register reads and writes, which is important, especially for debugging or figuring out how things work. Or I could just use this fancy software by the PYNQ and make it very easy. And it is very nice how this is easy. But the memory reads and writes are important when you start implementing your own hardware. So let's talk about the next step that we'll probably do in a different presentation, because I guess we'll just keep this one relatively short as well. The idea is that we would break this chain, break this loop back, and we could add in some hardware accelerator here, some processing. I think if I have, when will we do it? Probably next Monday or Tuesday. I think Monday I want to do PCIe. I've done a lot of cool stuff on PCIe, but Tuesday I think we'll do HLS here. And our goal is we're going to drop an HLS core right here. That's going to have an AXI stream in and an AXI stream out, and it's going to have a an AXI-Light interface. And what we're going to do is probably the first thing we're going to do is an adder, where we're going to assign a static or a one value over AXI-Light, and then we're going to add that value to all the values of going through the stream. So we can show how we can do rapid addition, vector addition, or something like that to the device, to our array that we're going through the stream. And that will probably be our step for next time. And this PYNQ makes it very powerful to test at, to represent it, to look at it. If we have time, maybe I'll go look at how to do Jupyter Labs. This is Jupyter Notebooks. Jupyter Labs, you can do a lot of graphing and whatnot. This is very powerful for do graphing and to represent your data. But right now, it's just really easy to peek and poke at this. Because I could pull up. We don't have the use thing in there, but I could pull up the SDK. I could go in and write these memory addresses myself and do this myself. And that would be interesting. And I could do all that read and writing that way and do it at the bare metal level. But it's really nice to see this in a Linux format where I have a nice, I can put in information, I can put in stuff and run these codes. Like I could insert little markdowns that explain each of these, which I probably should do. We'll probably do that. I'll probably do that later when I get to a better model. But that's how you use PYNQ. Really simple, really straightforward, and they keep improving it quite a bit. And I like it as a development platform. It allows you to make your own hardware quite easily, and it allows you to show off that hardware to be able to do rapid testing. I think a project I want to try, it'll probably be too far in the future. I want to do PYNQ and LightX. So LightX, yeah, let's just go to LightX. I want to incorporate the PYNQ software with the LightX hardware. So LightX has a bunch of these interfaces, and I want to be able to maybe write software. So first thing first is this is running on a Wishbone, and as we know, the processor runs off a AXI bus. This with Wishbone, we have an AXI. What's this do? Yeah, so we probably want to get an AXI to Wishbone converter, and then play around with, here, AXI-Light to Wishbone. Perfect. And that way we can try to incorporate the LightX with PYNQ. And I think that could be very powerful for testing, for running things, and yeah, overall. And if we could get the PYNQ software running on the VEX processor or another RISC-V processor, that'd be really cool. We'll see how that goes. That's not going to happen anytime soon, but it seems exciting. Okay. Are there any questions? I realize I have just one viewer at the moment. Do we have any questions? Are we good? Okay. So, let's see, the stream is almost 30 minutes. I think that's a good count. I need to upload my yesterday's video as well, so this has a good introduction. Yeah, I probably have enough time to get that up and going tonight. Yeah, overall, I think that's good. Well, thank you for joining us today. Hopefully these streams are helpful and provide you information, tools that are available and whatnot. Yeah, I'm just thinking about, so the PYNQ runs on a bunch of these really complicated, really expensive boards, right? But PYNQ is nothing, I would say, super powerful. If we could, say, define that for LightX, get LightX running Linux, and we can get that working on a Lattice board, on RD on probably a cheaper Series 7 board, like an RD board. Maybe get it running on, yeah. I'm gonna ask that to the people who do LIDX. Maybe look at their software. Okay, thank you for joining me. It's been 30 minutes. I should probably end it here. Good night.